In our last video, we looked at using Biot-Savart Law to find the magnetic field near a straight current-carrying wire. Now let's take a look at using it near a curved wire. Let's take a look at this problem. We're going to find the magnetic field at the center of a circular loop of wire carrying a current I. Here's the Biot-Savart Law. The first thing I want to do is get the direction of the magnetic field at the center of my current-carrying wire loop. Well, I have two techniques for doing that. Looking at the Biot-Savart Law, I can see that there's a cross product involved. ds cross r hat should give me the direction of the magnetic field. ds is a section of the length of our wire that points in the direction of current flow. I can pick this little chunk right here, or I can pick a chunk down here, or over here. I can pick any of those or any other place on here to pick my ds. Let's start with this one. R hat points from ds to my point of interest. Well, my point of interest is the center of this circle. So R hat points toward the center of the circle. If I'm at this other location, ds points to the right, R hat points toward the center of the circle. And if I'm at the third location, R hat still points toward the center of the circle. So at any of those locations, if you do the cross product, ds cross R hat, you should get out of the page. At any of those three locations, I can do the cross product, or any other location on this current carrying wire. I find my ds points in the direction of the current, R hat points from that location to my point of interest, and I do the cross product and I get out of the page. Now the other technique we could use is to use our right hand rule to find the magnetic field direction that encircles a current carrying wire. So we know this current carrying wire is going to fill the space around it with magnetic fields. And if I have a loop of wire like this, I know that a current running through that loop of wire is going to form magnetic fields that form circles around the loop of wire like this. If my current is going in this direction, that would be clockwise from your view. I can run my thumb in the direction of the current, and I know that any place on the inside of this loop, the magnetic field lines are going to be pointing away from the camera toward me. And anywhere outside of the loop, the magnetic field lines are pointing toward the camera, away from me toward the camera. So the magnetic field lines will form circles around the wire. And if I'm at the center, no matter where I am on my current carrying wire, the magnetic field will point away from the camera toward me if I'm using this loop. So let's do that with the one I have drawn on the page. I run my thumb in the direction of the current, and my fingers roll up out of the page on the interior of this loop. And on the exterior of the loop, they roll down into the page. So using this thumb in the direction of current right hand rule, I get the magnetic field any place inside is out of the page, and any place outside is into the page. So either technique gives us the right answer if we do it correctly. ds cross r hat, we know there's a cross product in this equation, we can use that. Or we can use our trusty right-hand rule for finding the direction of the magnetic field that encircles a current-carrying wire. Now let's take a look at finding the magnetic field using Biot-Savart Law. Let's start with ds cross r hat. Well, we've already talked about the fact that ds points in the direction of the current, so it's tangent to this circular loop of wire. And r points from ds to the point of interest, which is the center of the circle. So these two are always going to be perpendicular to each other. Remember, this is the magnitude of ds, the magnitude of our unit vector, which is just 1, and the sine of the angle we get when we put their tails together. In this case, that's 90 degrees. So the sine of 90 degrees is 1. The magnitude of a unit vector is 1. And so all we're left with is ds. The other nice thing about working on a circular arc length is that r is constant. So our magnetic field equation becomes and what is the integral of ds? It's just s, the total length of our wire. And s is equal to 2 pi r, the length of the wire, we end up with mu naught I over 2r. Now if you didn't see that the integral of ds is just the arc length, s, which is 2 pi r, let's take a closer look at what you could have done. ds is an arc length, right? It's a length of a segment, and in this case it's a curved segment, an arc length. And so what do we use for the length of the arc? We use r times d theta. R is constant. We're on a circular arc length, so the radius is constant. And in this case, we're doing a complete circle. We don't always do a complete circle. I could have drawn a current path that is only a quarter of a circle, or some other arc length. But in this case, it's a complete circle. So theta goes from 0 to 2 pi. And we get r times 2 pi, or 2 pi r, which is what we got earlier. So the magnetic field at the center, mu naught I over 2r, and the direction out of the page.